Welcome back, everyone. Today's explainer is all about demystifying exactly what happens under the hood when your high-level code stakes a claim on physical real estate inside your computer's memory. We are diving deep into Module 03, Understanding Variables and Data Types. Okay, here is our roadmap for today. We'll be hitting variables and RAM allocation, static versus dynamic typing, primitive types in binary, complex types in memory, typecasting and coercion, and we'll wrap the whole thing up with a hands-on Python blueprint. All right, Section 1, Variables and RAM Allocation. Let's get right into it. So I want you to think about this for a second. When you type x equals 5 into your code editor, where does that number 5 actually go? It's really easy to picture it just kind of floating around in the digital ether of your software, right? But it actually anchors into the physical reality of your computer's hardware. Think of your computer's RAM as a massive wall of sequentially numbered cubbyholes. Your variable name, whether that's my variable or just x, is simply a human-readable label for a very specific RAM address, like address number 103, for example. So when you set x equals 5, the CPU takes the binary representation of that 5 and physically slots it into one of those exact hardware cubbyholes. It's a physical location. Moving on to Section 2, Static versus Dynamic Typing. Now, different programming languages handle these cubbyholes in entirely different ways, and it's a fascinating contrast in philosophy. In statically typed languages, like C++ or Java, you absolutely have to explicitly declare your variable types before the code even runs, at compile time. This lets the compiler optimize the machine code for blistering speed. But on the flip side, we have dynamic typing, like in Python or JavaScript. Here, the type is inferred at runtime. This allows for what we call duck typing, which makes the language incredibly flexible and agile, allowing for much faster prototyping. Next up, Section 3, Primitive Types in Binary. Let's see how this builds. Here is a wild realization. The physical hardware of a general-purpose computer makes absolutely no intrinsic distinction between an instruction code, a text character, or a floating point number. To the CPU, it's all just raw bits. It's the language's type system that gives meaning to those ones and zeros. We've got integers for whole numbers, floats handling your decimals via the IEEE 754 standard, Booleans strictly restricted to true or false, and characters mapping bits to specific numerical encoding matrices like ASCII or Unicode UTF-8. Grasping this is exactly how you start optimizing your application's memory footprint. It's actually incredibly cool to see how systematically we can convert a standard decimal, let's take the number 47 for instance, into a precise string of binary bits. You just find the largest power of 2 smaller than your number, which is 32. You write down a 1, subtract 32 from 47 to get 15, and then you just continue down the place values, 16, 8, 4, 2, 1. For 47, you end up with 1, 0, 1, 1, 1. Toss on a couple of leading zeros, and boom, you have a perfect 8-bit byte. That exact binary configuration is what occupies the physical RAM cubbyhole we looked at earlier. Let's shift gears to Section 4, Complex Types and Memory. When we step beyond basic primitives, we have to talk about the 2 distinct pools of memory, the stack and the heap. The stack is automatically managed, super fast, and strictly for local variables using a last-in, first-out structure. But the heap? The heap is massive. It's managed via memory address pointers. It's a bit slower, but crucially, it allows variables to be dynamically resized during program execution. When we use non-primitive, complex types, the actual heavy-lifting data lives over on the heap, and we just keep a tiny pointer back on our local stack so we know where to find it. Strings and arrays are the perfect examples here. Under the hood, strings are really just immutable sequences of contiguous characters handled exactly like an array structure. And arrays themselves are zero-indexed ordered collections. Now, in strict, statically typed languages, every element in an array has to be identical. So all integers or all strings, but in dynamically typed languages like Python, you can literally mix and match integers, floats, and strings in a single list without the system even breaking a sweat. All right, Section 5, Typecasting and Coercion. Let's talk about what happens when types clash. We have all seen this warning sign, haven't we? The dreaded type error. This right here is the danger zone of unmanaged types. If you attempt to concatenate a text string with an integer without properly casting it first, your Python application isn't going to politely decline. It is going to throw an exception and crash hard. The CPU simply has no logical way to combine the word hello and the number 5. So to resolve these conflicts, we use explicit typecasting. Think of explicit casting as your ultimate translation tool as a developer. By using specific built-in casting operators, like wrapping a string of numbers inside an int function, you are manually forcing a safe data conversion. You are explicitly telling the runtime, hey, translate this string into an integer so my math operations can proceed safely without blowing up. And finally, Section 6, Hands-on Python Blueprint. Let's see this in action. Check out these examples of dynamic assignment happening in real time inside an IDE environment. We have user age equals 28, wallet balance equals 1250.75, is premium user equals true, and a user handle string. Notice how we didn't have to write the words int or Boolean or string anywhere? Because Python is dynamically typed, the language runtime just infers the required memory footprint automatically the exact moment we assign the value. It saves so much time and keeps your codebase incredibly clean. And we can actually prove it's working properly behind the scenes. If we run print type user age, the console outputs class int. If we run print ID user age, Python reveals the actual unique RAM address where that 28 is physically sitting in memory. And if we receive a raw input, like the string 500 from a user, we can explicitly cast it by typing int 500 to ensure our variables are mathematically ready before we calculate something like a total payout. It gives you total control. Which brings us to a fascinating final thought for today. We know the hardware sees absolutely no intrinsic difference between an instruction code and a floating point number. It relies entirely on the language's type system and our memory pointers to make sense of the binary bits. So, what do you think happens to our program and to our system memory as a whole if we accidentally lose track of our memory pointers in the heap? We'll leave that provocative thought right there for you to ponder before we dive into memory leaks in Module 04. Thanks for joining me for this explainer. Stay focused and keep coding.